Hello, this is Mr. Best. Welcome to Chapter 7, Homework Questions 108 to 114. What else can you prove about parallelograms? Prove that the diagonals of a parallelogram bisect each other. For example, assuming that the quadrilateral WXYZ below is a parallelogram, prove that line segment WN is congruent to line segment YM, and line segment ZM is congruent to line segment XM. Organize your reasoning in a flowchart, then record your theorem in your theorem toolkit. All right, so what are we looking at here? Well, we know that we're dealing with a parallelogram. So we know we have opposite sides are parallel, which cut by a transversal can tell us about alternate interior angles. So if we can prove that the triangles are congruent, for example, if we can prove that this triangle is congruent to this triangle, then we know their corresponding parts are congruent, which means this side length would be equal to this one, and then this one would be equal to this one. So that's kind of the route we're going to try to go, is we're going to try to prove triangles are congruent using the parallel lines so that we can prove that corresponding parts are congruent. So let's start with what's given to us. We know that line segment WX is parallel to line segment YZ. And that is given, or we can say that it's the definition of a parallelogram. We also know that opposite sides of a parallelogram are congruent, so we know that WX, line segment, is congruent to line segment YZ. And that is part of a, once again, knowing what a parallelogram is, and we have proven that the opposite sides are congruent. So we know that the opposite sides of a parallelogram are congruent. And then the other thing we can add on to this is we also know that with the parallel sides, if these lines are parallel, and we can kind of extend them, and here is the transversal, then we know alternate interior angles are congruent. So because the lines are parallel, we know that this angle, WXZ, so angle WXZ is congruent to angle YZX. And that's because of alternate interior angles. So that's because the lines are parallel, and the reason are alternate interior angles. We know they're congruent. We also know that this angle is congruent to this angle because with this transversal, all right, those are also alternate interior angles. So we also know that angle XWY is congruent to angle, let's see, so we got XWY would be congruent to angle ZYW. And once again, because alternate interior angles. So that comes off of the parallel line again. All right, I went ahead and moved that one fact bubble down a little bit there, but now what you'll notice is we have this angle and this angle congruent. We have this angle and this angle congruent. And then we also have the side lengths, the opposite sides congruent. So by angle side angle, we're able to prove that the triangles are congruent. So we're going to prove that right now. So that would be triangle WMX is congruent to triangle YMZ. And that's by angle side angle congruency. So now that we know the triangles are congruent, we also know their corresponding parts are, which means side XM is congruent to, where'd it go? Is congruent to ZM, and then WM is congruent to YM. And that's what we were trying to prove in the beginning. So from the triangle congruency, we now know that, once again, WM line segment is congruent to YM. So we know that. We also know that ZM, line segment ZM, is congruent to line segment XM. And so both of those come off. And we know that because we know that congruent triangles are going to give us congruent parts. So same thing over here. Congruent triangles means congruent parts. So now we have proved that, if we go back to the beginning here, we were trying to prove this, which we just did. And also, in terms of what we're looking at, we were trying to prove that the diagonals of the parallelogram bisect each other. So now we've proven that when you have a parallelogram, if you draw on the diagonals, they will always bisect each other, which means cuts it into two equal parts. So zoom out a little bit so you can see that flowchart proof. Question 109. One way a shape can be special is to have two congruent sides. For example, an isosceles triangle is special because it has a pair of sides that are the same length. Think about all the shapes you know and list the other special properties shapes can have. List as many as you can. Be ready to share your list with class at the beginning of lesson 7.3.1. So, I'll write a couple down, but really just think about all the different shapes that we've learned. What are some similarities? So this one right here said one of them is to have two congruent sides. We could add in, having right angles. Those are some things that we've had on some special figures of R, whether it's, a rectangle, a square. We have right triangles. Some other things that we have talked about. What about congruent diagonals? And so one of the things we proved about rectangles was their diagonals were congruent. We know we've talked about parallel. I spelled that wrong. I'll try that again. So parallel sides is another thing. We've talked about diagonals bisecting each other. We've talked about congruent angles. Whoops. So there's a few, but there lots more in terms of things that we've talked about. So just keep continuing to add to the list, and then when we get to lesson 7.3.1, that'll be part of the conversation. Question 110. Carefully examine each diagram below and explain why the geometric figure cannot exist. Support your statements with reasons. If a line looks straight, assume that it is. So starting with part A, but what we're looking at here, we have a length of 7, which matches up here. You have a length of 5, matches here, and then a length of 4 and matches here. So by side, they should be congruent. But if you look a little bit closer, the angle in between the 4 and the 7 is 80 degrees. So the angle in between the 4 and the 7 should also be congruent, which means it should be 80 degrees, and it is not. So they should be congruent by side congruency, but 80 degrees does not equal 50 degrees, so that's the problem. Part B, we have 40 degrees, 50 degrees, and so if we do vertical angles, this would be 50 degrees. And then when you go to find the third angle, it's 180 minus those two. And so this would be 180 minus 80, 100, so that means this would be 50 degrees here. But on this side, those add up to 90, so that means this angle right here would have to be 90. But you're looking at two completely different triangles with the angle measures. So even though you have, once again, what appears to be side, angle, side, so you have the side, the angle, and the side, the other angles don't match up in terms of congruent angles. So remember, congruent triangles have congruent parts, and that's not what we're seeing here. So we would have been able to prove it by side, angle, side congruency, but 90 degrees does not equal 80 degrees, or you could look at it the other way, 40 degrees is not equal to 50 degrees. So that's the problem there. On part C, we have what appears to be an isosceles triangle, but you have this side and this side, when you break it up, congruent. So you're looking at these two triangles, and that's a 12 and that's a 10. So right now, this side length is shared, so we know that's congruent to itself. So by side angle side, the triangles should be congruent. So once again, by side angle side, they should be congruent, but 12 and 10 are two different values. So therefore, since 10 does not equal 12, that's the issue that we're finding there. On part D, you have a triangle that appears to be isosceles because the side lengths are marked as being the same, but then you look at the angles opposite, and we have a 50 degrees compared to a 60 degrees. So even though the triangle should be, or is isosceles, should be isosceles by the lengths, the base angles are not equal. So we were looking at potentially having an isosceles triangle, but 50 degrees is not equal to 60 degrees. So the base angles are not the same. Are not equal or not congruent. Part E, really kind of dealing with the same thing here. This is a triangle that should be isosceles based on the side lengths, but the angles opposite them again are not congruent. So really, it appears to kind of be the same thing, except that one drew an extra line in there to mark that. But really the same thing. Is that we're looking at potentially what should be an isosceles triangle, but the 50 degrees, the base angle, again, they are not congruent to each other. And part F, we have a length of 15, a length of 15. We have an angle that is congruent, and then we also have the side length that they share in common using the reflexive property. So it looks like we have a side angle side congruency, but the corresponding part on the other side is not the same. So 13 does not equal 14, so that's the problem on that. Question 111. Remember that if a triangle has two equal sides, it is called isosceles. Decide whether each triangle formed by the points below is isosceles. Explain how you decided. So I put a couple graphs on here so we could use them just as kind of a visual. So the point 60 is here, the point 06, and then the point 66 would be right here. So if we kind of get a visual here of what this is going to look like, is it isosceles? Now this one's kind of nice because you can actually just count because you have you have a horizontal and a vertical line. So this would be 6 units, and this would be 6 units, and it forms a right angle. So yeah, you are going to have, for this one will be isosceles. You have, like I said, two sides, with length 6. And you can kind of prove that as I did on a coordinate plane there. Let's look at B. So negative 3, 7. So negative 3, 7. Plot that point. Negative 5, 2. And then we have negative 1, 2. So we're looking right here. Once again, it appears that it is isosceles. One of the things that we can do is kind of draw that line down there. And you can see that this is 2 units each. This is congruent to itself, and this is a right angle. So by side angle side, we do know that the two triangles are congruent, which means this length is equal to this length. We could also have done Pythagorean theorem to help us decide that. But that is one way. So we do know that once again, on B, it is also isosceles. Let's go on to C. C is 4, 1, so I'm going to go ahead and erase what I have here. And we'll plot the point 4, 1, the point 2, 3, and then the point 9, 2. And so if you draw this one in, just by the picture itself, it definitely appears that it is not isosceles, and I think you can see that pretty clearly. To go through and really show that it's not isosceles, we would have to find the distance between each of these points, but I think this is enough information to clearly show that part C is not isosceles. we will definitely get into how to show and go through and do all that work to show that it's definitely not isosceles. The only one that even appears that it might be close would be, see if I can mark this. This length might be close to this one, but once again, when you look at it, if you just kind of squeeze them together, you can see that that other side is definitely going to be shorter. And let's move on to D. Let me get rid of that. D, we have 1, 1, 5, negative 3, 1, negative 7. So here, here, and here. And so what we can do is, if we're going to prove that this is isosceles or look at it, it looks like this one and this one are the ones that would have to be the same. So if you kind of draw in the right triangle that is formed with that length, so you see this right angle and this right angle, this has a length of 4, this has a length of 4, so then you could find that hypotenuse. This down here has a length of 4, and this also has a length of 4. So we don't even actually have to find the hypotenuse's value because that triangle is exactly the same as congruent to this triangle here, then the hypotenuse would have to be the same. So once again, this one is isosceles as well. And so that finishes up identifying whether it's isosceles or not isosceles. Question 112. For each pair of numbers, find the number that is exactly halfway between them. So, just to give us a little visual here, we have 9 and 15. So, we also have 10, 11, 12, 13, 14. So we could just work our way in. There's 1 unit. There's 2 units. There's 3 units. And so right here would be halfway, which would be 12. So that's one way to look at it, is just kind of get a visual. What is happening? If I go 3 to 27 and the numbers are getting even larger, how do we figure out where that middle ground is? Well, you can look at the difference between the two, which would be 24 in this case. And so if the difference between 27 and 3 is 24, then that means you need to split that difference. So I'd have to go 12 in this direction, and I'd have to go 12 in this direction. Well, if I add 12 to 3, that would give me 15. And if I add 12 to 15, that gives me to 27. So 15 is the middle there. So that's another way to look at it. And then another way, just kind of showing you 3 different options here, 10 and 21. So here's 10, and here's 21. And so you could still do the difference of them, which is, 11, and then half of 11 is your 5.5. So you could do it that way. And then the other thing that you can do is you can actually average them. So if I take 21 plus 10 and divide it by 2, so that's 31 divided by 2 gives me 15.5. So that's another way where if you add the two numbers and divide by 2, it kind of averages them out and finds that middle ground that you're looking for. So hopefully I was able to show you 3 different ways to find the midpoint or find the exactly halfway in between numbers. Question 113. Penn started the proof below to show that if line segment AD was parallel to line segment EH and BF line segment was parallel to line segment CG, then A must be equal to D. Unfortunately, he did not provide reasons for his proof. Copy his proof and provide a justification for each statement. All right, so here we go. The first one is the given. That was given to us that the lines were parallel. So AD and the line EH are parallel, and then BF and line CG are parallel. So that was given. A is equal to B. So if we look at this, angle A is equal to angle B. And you can see that those are alternate interior angles. So we can say if the lines are parallel, then alternate interior angles are equal. All right, and then B is equal to C. So let's see, this is B right here, and then C is here. So once again, now that one with the parallel lines, those would be corresponding. So on this one, if the lines are parallel, corresponding angles are equal. All right, now we say A is equal to C. And if you notice that A is equal to C, those are on, whoops, didn't erase. A is all the way over here, and C is all the way over here. And the reason we know A is equal to C, well, if you look at this, if A is equal to B, and B is equal to C, then I should be able to replace the replace the B with the value of A. And so A is equal to C. And the way we're able to give a reason why this works is because of substitution. We are able to substitute the value of A in for B and get A equals C. So it might be a new one that we haven't maybe talked a lot about, but that's how that works, is that you can use substitution. And now we know C is equal to D, so let's go to that one. I've got quite a mess going on here, so let me clear that up a little bit. C is equal to D, so that's right here and here. So we know that's true because of vertical angles. All right, and vertical angles are equal. And then we know that A is equal to D, which is what we were trying to prove in the beginning, that A was equal to D. So now A, and remember, A and C are equal to each other, so then C and D are equal to each other. Then that means A is equal to D, once again, because of substitution. So kind of gets back to A equals C, and C is equal to D. Then I can replace the C with the value of A, and so therefore A is equal to D. So there are the reasons for what Penn started his proof to show that the two lines that are parallel, so two sets of lines that are parallel, also make A and D equal. Question 114. After finding out that her kitchen does not conform to industry standards, Lashea is back to the drawing board. Where can she locate her sink along her top counter so that its distance from the stove and the refrigerator is as small as possible? And will this location keep her perimeter below 26 feet? Show all your work. So going back to question, it was the speaker question. It's kind of the same idea. We're trying to find that shortest distance. So if we reflect the triangle over to this side, that will make this distance 3. Same distance as it is here. And then you have this is 6. And so you create this shortest path. And so this distance right here we can call x. And since that whole distance is 11, then we can say that this distance over here is 11 minus whatever that x value is. And these triangles are similar, so we can set up proportions. So the distance for 3, right here, let me change colors, 3 is corresponding to this side of 6. And then the length of x right here is corresponding to, x is corresponding to this length, 11 minus x. And so when we set up a proportion, we can solve for the x value. And so this will be 6x is equal to 3 times 11 minus x. We can go ahead and use the distributive property to get 33 minus 3x. And then we can add 3 and then divide by 9. So 33 divided by 9 is equal to 3.6 repeating, which is 3 2/3. And so we know that the shortest distance from the corner in terms of the stove from the right edge should be 3 2/3 feet. From the right edge. Now, that's the shortest distance. So then, is the perimeter below 26 feet still? So we need to add the 3 2/3 feet. We also need to figure out the distances of each of these. So we will have to use Pythagorean theorem to figure out these distances and then add that up. So since we know x is equal to 3 2/3, that's 3 2/3 here. 11 minus 3 2/3 is 7 1/3. So we can use Pythagorean theorem to be able to solve for this length and this length. So let's go ahead and do that. We have 6 squared plus 7 1/3 squared is equal to, we'll just call this y, is equal to y squared. So when I plug that in, I got approximately 89 point, it looks like 7 repeating, and then you can take the square root of that. So then y will be approximately 9.475. So that would be the y value. Now we can go ahead and do the same thing with the other triangle, but that gives us 3 squared plus 3 2/3 squared is equal to, we'll call this one z. So this is equal to z squared. So plug that in your calculator and see what you get. And so z squared is equal to 22.4 repeating. Take the square root of both sides, and z is approximately 4.738. Alright, now that gives us two of the distances. We still need the third distance. And if you go back to question 84, you'll notice that they gave us this angle in question 84, and we don't have that. So what we're going to have to do is we're going to have to use our trig ratios to figure out these two angles of the right triangle to figure out that third one. So let's go ahead and do that. So we can use the tangent, and I'll just call that theta, is equal to opposite, which would be 3 over adjacent, and that's 3 2/3. So to do that, remember you have to do the inverse of it to figure out what that angle is. Make sure you are in degrees and plug that in your calculator. So I have theta to be approximately 39.3 degrees. And then we'll do the other angle, tangent of theta, is equal to, probably should use a different variable, but that's alright. Tangent of theta is equal to opposite, which is 6 over 7 1/3. Once again, use the inverse, plug that into the calculator to figure out the other angle. And since I wasn't really thinking when I decided to plug all this in, I forgot that when these are congruent to each other because of those being actually the reflection of each other. So they are both 39.3 degrees. So if you take 180 minus 39.3 minus 39.3, or 2 times that, that'll give you the angle that we need. And so this angle would be 101.4 degrees. I put percent, whoops, 101.4 degrees. And so now we can use the law of cosines to find the last length. So we'll call this c. So c squared is equal to, find my values over here, 9.475 squared plus 4.738 squared minus 2 times 9.475 times 4.738, scoot this over, times cosine of the angle, which is 101.4 degrees. So plug all that in your calculator and then take the square root of it. So I get a value of approximately 129.97. Go ahead and take the square root of that, and we get C is approximately 11.4. And so now when you add all those angles back up, now when you add up all the side lengths, we're going to get some room here. We'll take the 9.475 plus the 4.738 plus the one we just found, which was 11.4. And if we are rounded 3 places, it was 0, 0. And you add all those up and you get 25.613. Remember, it was to be less than 26 feet, and it looks like it worked. So, and will this location keep her perimeter below 26 feet? And the answer to that is yes. It will, just by a little bit, but it does work. This is the way I approach this problem. Maybe there's another way to look at it, but this is kind of what I saw. So if you're looking at it a little different, that's perfectly fine. Once again, at the end, though, the perimeter should be somewhere around 25.6 feet.